change in momentum. We already talked about momentum, so it's actually still, it's going to be the same units. Impulse is actually the same units as momentum, okay? But we're going to talk about when velocities change and what happens. So first, impulse, the formula for impulse. We'll write impulse is triangle, which is also called delta, delta P. This is what impulse is. It's not, we don't use the letter I, we use delta P, which means the change in momentum. The triangle means the change in momentum, because we already used the letter P for momentum. So the change in momentum, or impulse, is equal to mass times the change in velocity. So far, so good? Okay. So anything that moves along, a baseball is flying through the air. It has a mass and a velocity. Let's make up a number. Let's say it has a velocity of 30 meters per second. And then it stops. How much did the velocity change?
A lot.
30, right? That's an easy number. Went from 30 to 0, changed by 30. So the change in velocity right here will be 30. If a baseball has a mass of 0.2 kilograms, all you have to do to get impulse is, if I gave you mass and velocity, do 0.2 times 30. And get your number. Okay? Pretty much every velocity I'll give you, there's going to be a couple where I say it goes from 7 to 5. If the velocity went from 7 to 5, what would you say the change in velocity is there?
2.
2. Okay? So it's just the change in velocity. A lot of times it'll be something to 0. Okay. So that's not too bad, right? Now, there's also another formula for impulse, though. Impulse, again, the change in momentum is impulse. Impulse is also force times time. So the impulse of that baseball stopping will be equal to the force times the time of my hand catching the ball. The force that my hand has to stop that ball, and for however long it takes me to stop that ball, will be equal to the impulse it had. Okay, so mass times change in velocity, impulse, will be equal to the impulse, or the force times time, that my hand has to stop the ball with. So there's two formulas with impulse. I will have a question on a test like this. Mass times change in velocity, and you just multiply it. I will have a question like this. I give you a force and a time, and you have to calculate it. But both of those are actually really boring. Both of those are kind of useless if you just say, what's the impulse? I don't really care what the impulse is. But here's what's really important. Here's what's actually useful. Because they're the same thing, you can say they're equal. So I can say that mass times change in velocity is going to be equal to the force times time. The impulse that I catch that ball with will be equal to the impulse that the ball had to stop with. I'll pause it there for station identification. And we're back. We should be on TV. Alright, now here's the most important thing though. So the idea is that, let's say with a baseball, no matter what, the mass times the velocity that changes is going to be the same number. So no matter what happens, no matter how the baseball is caught, it's going to have the same impulse. The number is going to be the same here. But I could catch it two different ways. If I have a baseball flying at me, I could catch it barehanded, keep my hand like this, and just try to grab it when it touches my hand. How's that going to work out?
Not very well.
Not too much, right? It'll hurt, and it'll probably bounce out of my hand. But if I wanted to do that, I could catch the ball with a really, really short time. I just hold it out and do that. It's going to be a split second to stop that ball. It's going to be a really small time. That means there's going to be an extremely high force on my arm and on my hand and on the ball. The ball is going to bounce out. Or I could catch it with a glove and give. Right? So instead of catching like this, I could give. The ball touches my hand and I give with it. Okay? I increase the time it takes to stop. So instead of a split second of it stopping, or 0.0001 seconds, it's only a half a second now. It's a lot bigger of a time. There's going to be a much bigger time, so there'll be a lot less force. I'll be able to catch the ball if I increase the time it takes to stop, than if I just try to do this and have a really short amount of time. That's a key concept I want you to understand today. The key concept today is this. If the time goes up, if I increase the time it takes for something to stop, the force goes down. When you increase the time it takes to stop something, the force goes down. When the time goes up, the force goes down. Why don't we repeat that? Everyone repeat that. When the time goes up, the force goes down. That was awful. Repeat after me. When the time goes up, the force goes down. So here are examples of that. Back to the baseball, let's talk about football. All right, wide receiver is going to catch the ball. They're trained. Wide receivers are trained and practice that when they're warming up, they give. So they hold their hands out and they give. They're not going to try to catch a football like this. Okay, if they try to catch it like that, it's going to bounce out of their hands. So they make the triangle, but as they catch it, they're going to give. And you'll see them even warming up and they're doing this, practicing to give. They increase the time it takes to stop. So they decrease the force on the ball, so it's not going to fly out and bounce out of their hands. Okay, soccer. Okay, well, goalies too, they're going to give. But soccer with all the other players, a chest trap. If a ball goes to your chest, a soccer player's not going to do this. Okay, because the ball's going to hit your chest and bounce to the other team. So soccer players, they want the ball to be trapped and go to their feet. So instead of this, they're going to give. All right, the ball's going to hit and they're going to give in. So they've increased the time it takes for that ball to stop, and the force has gone down. So instead of the ball bouncing to the other team, it drops to their feet. Okay, same with their feet too. Okay, where they're not going to hold their foot straight out and let it bounce off, but they're going to give. They're going to let the ball come in. They're increasing the time it takes to stop to decrease the force. Pretty much any sport. Yes, ma'am?
Sometimes you do let it bounce off of you if your teammate is right in front of you.
If we're going to pass it, sure. But most of the time, when you drill, when you learn in kindergarten or whenever you started playing soccer, the first thing you're going to be taught to do is to give, right? Decrease that. Yeah. Right. So that's any other sport. There's going to be an example of impulse. Okay, so with wrestling, we have wrestling mats. Because when I slam somebody, they need a little bit more time to stop. Okay? Lacrosse, catching, any sport you need to catch the ball, the coaches will be teaching you to give. Football pads, even the pads themselves, are made to increase the time and decrease the force. Okay, so we have plenty of sports analogies. What about with cars? Are there any examples with cars where you increase the time and decrease the force?
When you're braking.
When you're braking. When you're braking, you don't want to stop on a dime. If you stop the instant you touch the brakes, your car would stop immediately and you'd keep going. All right, and there'd be a lot of force on you. So cars are not designed to stop on a dime. What about in a car accident? What's designed to increase the time to decrease the force?
The crumple zone.
You beat me to that. Yeah, I was gonna do airbags first. But yes, let's talk about crumple zone. Your car is actually designed to crumple in. The front of your car and the rear of your car is supposed to crumple. Because if you had a car that's built like a tank, if you hit a wall or a tree, the car would stop instantly, but your body would still be going, and there'd be a whole lot more force on your body. Okay? A crumple zone is designed to crumple in, absorb the force of the car of the crash, and increase the time it takes to stop to decrease the force on you. That's what crumple zones are for. Okay? Airbags are the other one. With an airbag, an airbag is not designed to inflate and stay inflated. That would be very bad. An airbag, if you hit the airbag and then bounce off the airbag, you have twice as much force on your head. Because not only did you have to stop, you had to go the other way. You don't want to do that. So an airbag is designed to immediately start to deflate. Your head hits it and it's already deflating, so you're slowly brought to a stop. Have you ever seen like the stuntmen that jump off a roof and into one of those big airbags? Right? They have big, huge flaps that as soon as they hit the airbag, flaps open up and all the air gets let out. If they weren't there, they jump it onto the airbag, then they bounce off the airbag and hit the curb. Right? And that wouldn't be good. But even before that would happen, the fact would be if they had to be changed, if their direction got changed from the airbag, that alone, that bounce there would be very painful. Okay, and that's why they deflate. Okay? Alright, so that's what we're talking about today. Again, if you increase the time, you decrease the force. When we do the egg drop next class, first I'm planning, hopefully I'll have it set up, I'll have a sheet set up, and you can throw eggs at the sheet if you'd like to. Okay? You throw an egg against the sheet, and you'll see that the egg won't break. If you throw an egg against the wall, the egg will break.
Do you throw the egg at a wall?
No. And if you miss the sheet, then you clean up the egg. Yes.
Didn't we already see that in the video?
Yeah, kids did video of that because I did the demonstration or done the demonstration before. Yep.
Slinky.
All right, that's it.